All right, this lecture is entitled Kinetics 2. Probably should be not using Roman numerals because there's going to be so many lectures here. Anyway, Kinetics 2, and this is a continuation of the topic of determination of rate law. We're going to go through a couple examples here. You saw the first example on the last video entitled Kinetics 1. So now we want to do this again, a new reaction, new rate law, and the reaction is for chloromethane in water reacting to form methanol and HCl. So the question is, what is the rate law given the following information? All right, so then you'd be given a table with some data, and because there are two reactants, we're going to need to do 3 experiments to figure it all out. You can make a table, or actually you'd be given this table where you have concentrations of your reactants and then values for the rate, which have units of molar per second. Of course, the brackets around the substances means molarity or molar. Let's see what else here. Okay, so then you need 3 experiments. Experiment 1, experiment 2, and experiment 3. Okay, and the data is 0.20 moles per liter, 0.20 moles per liter, and the rate turns out to be 1.5 molar per second. How do you determine the rate? You have to do an experiment where you plot the concentration versus time. You would take the change in the concentration and then divide by the change in time to figure out the rate. All right, now you do a second experiment, and this time you double the concentration of the chloromethane relative to experiment 1, and you leave the concentration of water the same. What we're doing here is it's referred to as the isolation method, and you want to figure out what the rate is associated with the chloromethane. If you double the rate of the chloromethane, how does the rate of the reaction change if the water itself stays the same? So it's just a way to kind of leave water the same, isolate out that chloromethane and look at its behavior. And we would find if we double the rate, double the concentration, then the rate will double. Then you do a third experiment where now you want to look at the behavior of water. So you go back to experiment 1 and you leave the concentration of chloromethane the same, and now you're going to double the concentration of water and do another graph. You're going to look at change in concentration divided by change in time at different intervals to come up with the rate, and the answer is going to be 6.0 molar per second. All right, so that's your data. That's what you're going to work with. And you write a rate law first, kind of the general form of the rate law. Rate would be equal to K times chloromethane concentration raised to the power M, and then water concentration raised to the power N. So you want to figure out the values of M and N first by these concentration differences and the rate differences. And then in the end, you're going to go back and plug in all this information to calculate the value of K like we did in the last experiment. Okay. So in general, we see that the ratio of the concentrations raised to the power m will be equal to the ratio of the rates. So this is going to be an important equation to work with. Get you some quick information just by plugging things into this. So if we do that, then let's go ahead and compare experiments 2 and 1. So compare experiments 2 and 1 next. And you can look at the concentration of the chloromethane in experiment 2. You're going to divide that by the concentration for experiment 1, and then that'll be raised to the power m, and then you take the ratio of the rates as well. So it'll be 3 divided by 1.5. So using that equation, we'll say 0.40 divided by 0.20 raised to the power m is equal to 3.0 divided by 1.5. So we're going to get 2 to the power m is equal to 2. Therefore, m has to be 1. So in our rate law, then the power associated with the chloromethane concentration, that power is going to be equal to 1. Now you could have looked at this data and said, okay, if I leave the concentration of water the same here, and if I double the concentration of the chloromethane and I see that the rate doubles, then there's a linear relationship between them, and the power has to be 1. But if you want to be a little bit more systematic about it, you can use this equation right here, which is what I just did. Okay, so then the next step is to compare experiments. In this case, we can look at 3 and 1, because if you compare 3 and 1, then you have the chloromethane concentration the same, and you're doubling the water. And you can just look at that table and say, okay, if I double the water concentration, it's a 4-fold increase in the rate. Therefore, n has to be equal to 2. But let's do it systematically. So we're going to say 0.4 over 0.2, 0.40 divided by 0.2 raised to the power n, and that will be equal to 6 divided by 1.5. So you're going to get 2 to the power n is equal to 4, and therefore n will be equal to 2. All right, so we've done this isolation technique where we've done one reactant at a time while holding the concentrations of the other reactant constant. All right, now we can go back and write the rate law again. So rate will be equal to K times chloromethane concentration to the, whoops, that should be brackets there, raised to the first power times water raised to the second power. So that is the rate law, but when I ask you to give me the rate law, we're not finished yet. What you want to do now is solve for K. So K will be equal to the rate divided by the concentration of chloromethane and divided by the concentration of water squared. And with this, you want to take care of your units as you're going along. The units are part of this whole thing. Now, let me scroll back up to the table just for a second here. And the comment here is that you want to substitute your data into that last equation so that you can calculate K. So if you have correctly determined the rate law, in other words, you've got your powers 1 and 2 for this example, if you've done it correctly, then it should be that you can substitute the values for experiment 1 into that equation and calculate K, or you could substitute the values of experiment 2 or 3 into that equation for K, and you should get the same value of K for each of those three calculations. You don't have to do that, you just have to do one calculation. But if you want to check and make sure that your rate law makes sense, that data should work for each. You should get the same constant K for each calculation. All right, so let's have a look at that. So let's go ahead and use the information for the first experiment. And we're going to say the rate is 1.5 molar times seconds to the minus 1, or molar per second. We're going to divide by 0.2 molar and 0.2 molar squared. Calculate K, 190. And then here you need to look at these units and see the logic in its determination for the final result. In this case, one of the molars is going to cancel. You have molar squared in the denominator. You have seconds to the minus 1. So the units for this one are going to be molar, to the minus 2 times seconds to the minus 1. Okay, that's how you get that. Next, you go back and put it all together. Rate will be equal to 190 molar to the minus 2 seconds to the minus 1 times the concentration of chloromethane to the power 1 and water concentration squared. So that is the rate law, and this would be the final result that I would be asking for on a test. Now the 1 for the chloromethane, you can leave that 1 out. Most people do. 1 is assumed. Now a little bit of detail here. I kind of hesitate to do this, but on the other hand, you're going to run into problems where this perspective might be helpful. So some people kind of prefer to do the same analysis that we just did this way instead. So let me just say detail here, and if you don't like it, just ignore it. You don't need to do this in order to work out these problems. You can just do the other simple methods that I'm showing you. But anyway, let's just take a minute, look at this. So we can say rate for the first experiment is equal to K times 0.20 raised to the power m and 0.20 raised to the power n, and that rate is 1.5 molar per second. Then you can look at a second equation for rate. This would be for experiment 2. So rate 2 would be equal to K times 0.40 raised to the power m times 0.20 raised to the power n, and that is equal to 3.0 molar per second. Similarly, rate 3 will be equal to K times 0.2 raised to the power m and 0.4 raised to the power n, and that is 6 molar per second. Okay. Then you can take ratios, and you could say rate 2 divided by rate 1 would be equal to K times 0.40 raised to the power m times 0.20 raised to the power n, and then that would be divided by K times 0.20 raised to the power m and 0.20 raised to the power n, and that will be equal to 3.0 divided by 1.5. The units are going to cancel there. So also you have, if you're comparing rates 2 and 1, remember the concentration of water stayed the same, so there's no difference, and if you take the ratio of those concentrations, that's going to be equal to 1. Also, the rate constants cancel here, and then you end up with 0.40 divided by 0.20 raised to the power m is 3 divided by 1.5, and so you have 2 to the power m is 2, and m equals 1, which is exactly what we got before. Then you can take your rate 3 and divide by rate 1. Just do it again. So you can say rate 3 divided by rate 1, and that will be equal to k times 0.20 raised to the power m times 0.40 raised to the power n, and then that'll be divided by k times 0.20 raised to the power m and 0.20 raised to the power n, and that'll be equal to 6.0 divided by 1.5. So the units I didn't write down for the rate, they cancel anyway, and now you got the concentrations of the chloromethane canceling. We can look at the water here, the water relationship. So we'll say 0.40 divided by 0.20 raised to the power n is equal to 4. So you've got here 2 raised to the power n is 4, so n is going to be equal to 2. So it's exactly the same result that we got. It's just that it's a little bit more systematic in the approach, I suppose, but it can be longer and a little bit more tedious as well. Okay, so that is the second experiment, and I'm going to show you the third experiment now. Okay. So experiment 3, the first one was on the last lecture. This one is for peroxide, H2O2, reacting with 3 iodide plus 2 H plus, forming I3 minus. That's called triiodide. It's yellow in solution, and it's not very stable. It disappears quickly and goes back to form I minus and I2, but that's another story. So the problem here is to find the rate law. Given the following information. Oops, that's an N there. Given. And we have peroxide, iodide, H plus, and then rate in units of molar per second. And because you have 3 reactants on the left, you're going to need 4 experiments for this one. Excuse me. Experiment 1, experiment 2, 3, and 4. Okay, and the data here is 0.010, 0.010, 0.0050, and the rate 1.15 times 10 to the minus 6 molar per second. Second experiment, we're going to keep the concentrations of 2 of these the same, and then we are going to vary only one, the third one. So we'll start by doubling the concentration of the peroxide in our second experiment, leaving the concentrations of iodide and H plus the same. So it's 2.30 times 10 to the minus 6 for the rate if we do that. All right, experiment 3, and this is where it gets a little tricky. We're going to go take the peroxide back to what it was originally in experiment 1, and now we're going to double the concentration of iodide, 0.02, and then we're leaving the concentration of the H plus the same. So we've changed this only relative to experiment 1. relative to experiment 1, and leaving these constant. So then the rate for this one is the same, 2.3 times 10 to the minus 6. All right, and then finally, comparing to experiment 1, we're going to leave the peroxide concentration the same as it was, the iodide concentration the same as it was in experiment 1, and we're going to double the concentration of H plus relative to it in experiment 1. So 0, 1, 0, 0. Then the rate on this one is 1.15 times 10 to the minus 6. Okay, kind of messy there. Now we are going to take the shortcut method and figure out the relationship for M, N, and P. So we're going to compare experiments 2 and 1. So we are going to look at the change in the concentration of the peroxide versus the change in the rate. So we'll say 0.02 divided by 0.01 raised to the power m, and that will be equal to 2.30 times 10 to the minus 6 divided by 1.15 times 10 to the minus 6. So we're going to get 2 to the power m is equal to 2. So here we get m is equal to 1. So 2 to the power 1 is equal to 2. All right, I should have written this first. You want to write out the rate law for this reaction. It's going to be K times the concentration of peroxide raised to the power m, concentration of iodide raised to the power n, and the concentration of H plus raised. And we're not going to use O because it looks like 0, so we're going to say P there instead because you have 3 reactants. All right, we just figured out 1. Now we're going to compare experiments 3 and 1, and we're going to compare the rates of those two. Okay, so we're going to compare experiment 3 and 1 for this. So it'll be 0.02 divided by 0.01 raised to the power n will be 2.3 times 10 to the minus 6 divided by 1.15 10 to the minus 6. Okay, let me find that in my notes here. Okay, I got that right. So 0.02 divided by 0.01 raised to the power n will be 2.3 times 10 to the minus 6 divided by 1.15 times 10 to the minus 6. And we're going to get 2 to the power n is equal to 2 again. So n will be equal to 1. So m is 1 and n is 1. Then we're going to look at, let's go back up to the table. I'm going to use a different color here. So to get the H plus concentration, we're going to compare 0.01 from experiment 4 to 0.005 from experiment 1. We're going to divide the rates 4 and 1. All right, so do that here. We're going to compare experiments 4 and 1. So I got that right here. 0.0100 divided by 0.0050 raised to the power p will be equal to 1.15 times 10 to the minus 6 divided by 1.15 times 10 to the minus 6. And then you have 2 to the power p is equal to 1, what does P have to be? P has to be equal to 0. So 0 order on the acid, the H+. All right, let me make a note here before we put this all together. It's not always so obvious that you know, whatever you get as your ratio raised to some power is equal to some number. In this case, you can just say, well, okay, it has to be 0. 2 to the power 0 is 1. But it's just the numbers are not always that clear cut. You know, they are for an example. We're just trying to teach the points, but in truth, it can be a little bit more, I don't know, complicated, I guess. So here is a technique. If you have 2 to the power, 2 to the power P is 1, which is what you just had there. You can take the logarithm of both sides. So the logarithm of 2 to the power P is equal to the logarithm of 1. Then you take this little p right here, and this becomes multiplicative. So the laws of logarithms say that if you got a power, taking the logarithm of something with a power, that you can write it on the left-hand side as the multiplier. All right, so then this is going to be equal to p times the logarithm of 2, and that'll be equal to the logarithm of 1. So in general, you know, solve for p, logarithm of 1 divided by the logarithm of 2, and that is not the same thing as the logarithm of 1/2. You know, you're not necessarily using logarithms every day. You might want to say that that's the logarithm of 1/2. It's not. It's the logarithm of 1 divided by the logarithm of 2. So in this case, p is going to be equal to 0 because the logarithm of 1 is 0. Okay, so in the group activity, you're going to be doing this on one of your examples, and I think you might find out that there's a fractional value for the order, like 3.5, 2.3, that kind of thing. It's possible to have non-integer values for the order, so you could see that in many different experiments. Anyway, okay, so now we're going to put it all together. And we're going to say here that the, where were we? Next page. So rate then is equal to K times the concentration of peroxide raised to the first power, iodide raised to the first power, and then H plus raised to the power 0. So of course that is equal to 1. So then we can rewrite that and say rate is equal to K times the peroxide concentration times the iodide concentration, right? And next step is to solve for K. That is equal to the rate divided by the peroxide concentration and divided by the iodide concentration. You can pick any one of those 4 experiments and take the data going across and plug into this expression to get K. And it doesn't matter, you should get the same value for K as long as your rate law is correct, as long as your orders are correct. Okay, so now we're going to say K equals the rate, 1.15 times 10 to the minus 6 molar per second. Oops, I don't need that. Yes, I do. Okay, and then divided by peroxide concentration from experiment 1, 0.010 molar and 0.010 molar. They're both to the first power. Okay, now go through the unit analysis here. This is an important part of it. The molar in the numerator is canceling with the molar in the denominator. So then you have seconds to the minus 1, and then you got molars in the denominator, so that's molar to the minus 1. And you're going to end up with K being equal to 1.15 times 10 to the minus 2 molar to the -1, seconds to the -1. Then, if I've asked you for the rate law, you got to put it all together and give me the whole thing. So we're going to say rate then is equal to 1.15, 10 to the -2, molar to the -1, seconds to the -1, and then times peroxide concentration to the first power and the iodide concentration to the first power. And that's how you do that. Okay. So then, some more comments on the order. And so far, the experiments that we've looked at have involved doubling. So usually, the concentrations are doubled, but not always. And in fact, when you're in the lab, it's hard to get exactly double anyway, right? So not always. And let's just look at some different possibilities for this. If you have the relationship that the rate of 2 divided by the rate of 1 is equal to the concentration of 2 divided by the concentration of 1 raised to the power m. I guess I've been writing it the other way, but it doesn't matter. Okay, and so if the concentrations, or concentration 2 is double concentration 1, so if the I guess I want to say here, if the concentration for 2, write that again. If concentration 2 is double concentration 1, then you have the result that rate 2 divided by rate 1 is 2 to the power m, right? So the concentration 2 is twice that of 1. Then you can solve for rate 2 is equal to 2 to the power m times rate 1. So you can plug your numbers in there. And if m is equal to 1, then we're going to get that the rate doubles. So in other words, if m here is equal to 1, then rate 1 times 2 would be equal to rate 2. So the rate doubles. But you can look at other examples. So if m is equal to 2, then you've got 2 squared is 4. So rate 2 will be equal to 4 times rate 1. So you'd say here the rate quadruples. If m is equal to 3, then you're going to have 2 to the power 3 is 8. So I'm really not sure if octuple is the right word there. We'll say that the rate increases 8-fold. Or 8 times. But you can also go the other way and say if m equals 0, then you have 2 to the power 0 here is 1, so the two rates are going to be equal to each other. So we'll say here rate does not change. Right? But also you can get negative numbers for m. And what if we had m is equal to -1? What would that look like here? So if you've got a -1 as your power, what is that? 2 to the -1. So you've got the result here that 2 to the -1 is 1/2, right? 1 over 2. So this is saying that rate 2 is going to be equal to 1/2 rate 1. So it means it's slowing down. So rate 2 is 1/2 of rate 1. All right, so this all has to do with doubling. In every case here, we doubled the concentration. So for doubling the concentration, we do not have to do that. We don't have to double it. We could triple it. We could do anything we want. We could be 2.5. Whatever the numbers are in your lab, you can take the ratio of. But just to show you the example here, if the concentration is tripled, from one experiment to the other, then you're going to have the result that rate 2 is equal to rate 1 times, I should have put that, let me put that over here, sorry, equals 3 to the power m times rate 1 instead of 2. You're tripling instead. So then if you, let's see, so if m is equal to 1, then rate 2 would be triple. Rate 1. So it'd be 3 times larger than the rate for the first experiment. That's RATE right there. And just one more here. If m is equal to 2, then you've got rate 2 is 3 squared, which is going to be 8 times. Rate 1. So it gets a little complicated, but again, you don't have to triple. Maybe you in your lab you've got 2.5 divided by 1, something like that. So you can just plug it into this simple equation here. That what do? We just said rate 2 divided by rate 1 raised to the that ratio of rates is equal to the ratio of concentrations, which would be 3 raised to the power m, and you're trying to figure out m. So you may run into that in your travels. Okay, so I think I'll stop here and continue with Kinetics 3 in the next video. Thanks. Whoops, I don't want to do that.